Now, let's also consider variation across the period of elements. Is that okay? So I've explained moving down the group, the radius of the atom generally increases. But across the period, the radius of the atom generally decreases. So we are going to say that atomic radius generally decreases, moving from left to right across the period. The radius of the atom, so atomic radius generally decreases, moving from the left to right across the period. So moving from the left hand side across horizontally, there is a reduction in the radius of the atom. And how do we account for these as well? Now let's discuss these ones. So I have taken the period 2 elements. I have 3 examples: lithium, beryllium, and then boron. So this is lithium, this is beryllium, and then this is boron. Lithium, beryllium, and then boron. Now, let's go through our quick observation, what we can observe here. So we could observe that moving across the period from lithium, beryllium, and then boron, we have the same number of shells. They all have 2 shells each. So we have 2 shells here, 2 here, and then 2 here. Now let's also consider something here. We could observe that there is the same number of inner shell. So there is 1 inner shell here, 1 inner shell, 1 inner shell. And in addition to this, they have the same number of atomos or valence shell. They all have 1 valence or atomos shell. Now, what also can we observe? We can also observe that they all have the same number of inner shell or core electrons. So we have 2 core electrons in lithium. When we get to beryllium, we still have 2 inner shell electrons. Same applies to boron. It's the same across the period 2 elements. They all have the same number of inner shell. It means that the inner shell electrons that will be acting as the screening or the shielding agent is kept constant across the period 2 elements. Is that okay? Now, again, what can we also talk about? There is 1 valence electron in lithium, but in beryllium there is 2 valence electrons, and then also in boron there is 3 valence electrons. So let me clean the sodium diagram here and let's explain something. How many protons do we have here in lithium? In lithium here we have 3 protons. Is that okay? And in beryllium here we have 4 protons. In boron here we have 5 protons. So basically, once you're moving across the period, there is an increase in number of protons per each atom. So here we have 3 protons, but once you move on to the next element across the same period, we have 4 protons, 5 protons. There's going to be an increase in 6, 7, 8, 9 to 10. So 1, there is an increase in number of protons moving across the period. What is the implication of this? The increase in number of protons simply implies that there is increase in nuclear attraction moving across the period. Now, if nuclear attraction is increasing, what can bring about a blockage in this attraction? That is the inner shell electrons. But let's see whether they are capable of bringing about a reduction in attraction. In lithium, we have 2 inner shell electrons. That is going to cause the screening or the shielding. In beryllium, we still have 2. In boron, we still have 2. So we could see that across the period, in the period 2 element, for example here, the screening electrons are kept constant, but the proton attraction gradually increases. And we could also see that the proton attraction will exceed the screening electrons. So it simply means that once you're moving across the period, nuclear attraction or effective nuclear charge will increase because the screening electrons are kept constant and the nuclear attraction is greater than the screening electrons. So therefore, the pull of the valence electron will be great, moving across the period from one element to the next element. Is that okay? So across the period, the variation mathematically is that effective nuclear charge will be increasing while the screening effect will be decreasing, or it is kept constant. So the radius of the atom decreases, it becomes small whilst you're moving across the period of elements. Why? Because the inner shell electrons that we want them to bring about reduction in attraction, they are kept constant and their number is small compared to the proton attraction for the valence electron. So once that happens, the proton attraction will exceed the proton attraction will exceed the screening electrons, thereby pulling the valence electrons more onto the nucleus. And once that happens, the distance between the proton and then the valence electrons becomes very, very small. And this small distance gradually decreases once you're moving across from the left-hand side to the right-hand side of the periodic table across the period. Is that okay? It simply means that once you're moving here, the radius will be decreasing. So the radius in beryllium will be smaller than that of lithium because the proton attraction in beryllium is greater than that of lithium. Once you get to beryllium and then boron, the radius of boron will be smaller than that of beryllium. Why? Because the proton attraction in boron is greater than that of what? In beryllium. But the screening electrons are kept constant. So over here, we use the increased number of protons, which brings about an increase in attraction and effective nuclear attraction. Is that okay? So generally, across the period, the radius of the atom decreases because the screening electrons is kept constant, but the number of protons increases, and this increases the nuclear attraction for the valence electrons. Is that okay? Alright. So when you take out periodic table of elements, the radius will be decreasing. So nitrogen will have a smaller size than carbon. Carbon also have a smaller size than boron. Boron will have a smaller size than beryllium. Beryllium will have a smaller size than lithium. Same applies to the elements in period 3 and also in period 4 as well. Is that okay? There will be time for questions. This is the concept of atomic radius. Moving from top to bottom of a group, it increases due to an increase in increased number of core shells, electrons, which increases reduction and blockage in attraction from the protons onto the valence shell. So we say that the radius or the distance between the proton and its attraction for the valence electron gradually increases. But once you're moving across the period, there is only one inner shell for the period 2 elements and 2 inner shell electrons. So it is kept constant across the period. But there is an increase in number of protons. And an increase in number of protons means that there is an increase in number of nuclear attraction. Increase in number of nuclear attraction which exceeds the screening electrons means that there is an increase in effective nuclear charge. And while there is an increase in effective nuclear charge, the distance between the valence electrons and then the protons become very, very small. Is that okay? Alright, we shall meet again in our next lesson.